Remember when we started, yeah, okay, let me just turn, so can you see there's no voltage here? So that means electrons cannot be pulled across to the other side. Let's just start as we did the other day. We started with red light. Does red light have a very, okay, so I'm going to pick on people. Red light have a very high energy or a very low energy, Bianca?
Low energy.
You don't sound very sure. Yes, it is a low energy because it's got the longest wavelength. So the longest wavelengths there would mean that it has the highest energy. Yes. Then if we look across, come now. If we go across to this side, you will see if I move it, the wavelength is getting shorter. And if the wavelength is shorter, what is happening to the energy, Carly?
Increases.
The energy is increasing, because remember those two things are inversely proportional to each other because the speed of light is constant. It doesn't matter what color it is, it's still going to move at 3 times 10 to the 8 meters per second. Alright, so at the moment, no electrons are being emitted. So even if I put a current here, so you can see I'm putting a potential difference. So this one, you can see there has a lot of little negatives. I hope you can see it. A lot of little negatives. You can also go and play with it. And this one has a lot of little positives. So even though there's a huge charge, and I can make it as big as this battery wants me to go, it only gives me 8 volts, but electrons cannot all of a sudden start jumping. You have to set them free. So there is other ways of setting them free. I could heat them up. I could give them heat energy. If I give them heat energy, they will leave. They already knew this before Einstein. They already knew that because if we heat this up, the electrons will gain energy and then it will be called thermionic emission or thermoelectronic emission. But we're not doing that here. We're not heating them up. We are giving them energy using light. So if light was a wave, and that is the important thing here, if light was a wave, then a little electron sitting here would sit there and gather energy, gather energy, gather energy until it had enough and then it would leave. But when they used red light, that never happened. So that was one of the things they expected to happen and it never happened. Because never ever did red light kick electrons out or emit electrons. So they realized that it's a one-on-one interaction, and that's when they started thinking, maybe there's a particle involved here, we've done that, which they then called quanta, which is packets of energy, and those packets of energy then we called photons. So the only way I can get electrons to leave from a specific metal, so at the moment I'm using sodium there, so from a specific metal, is to actually use light with a higher energy. So even if I put the intensity of the red light, remember what intensity is. Intensity just means I'm sending more photons. So a sharper light just means more photons per second. Intensity is per second. More photons per second is going onto that metal. But still, those photons don't have enough energy, so the electrons are not emitted. But now, if I want the electrons to be emitted, I think it's yours next to me, yes. What must I do now if I want an electron to be emitted? Jimmy, can you hear me? Jimmy, are you typing? If you're typing, put your hand up. Or if you can hear me, put your hand up. Okay, I'll get back to me again. Can you please help me, Kavan? What must I do if I want an electron to be emitted there?
I think the light needs more energy, something like that.
So how do I do that? How can I give that light more energy?
I think the wavelength needs to be shorter.
Okay,
right?
So if it stays on orange like it is now, orange light will always have that wavelength. So that means it's not going to help if I keep on shining orange light onto it, because orange photons only have that specific amount of energy. Even if I'm sending thousands more, it's not going to help. So I have to change the wavelength, and to change the wavelength I actually have to change the color. So now you can see the wavelengths are going shorter, which means the energy is going higher, but still no electrons are being emitted. Tumi, are you back?
Yes, ma'am.
Please tell me, why will this green light still not emit an electron?
The minimum energy required to emit an electron isn't met.
Okay, oh yeah, I like the way you say it. The minimum energy that the electron required is not met. What do I call that minimum energy that the electron require?
The work function.
The work function. Good. So we haven't met the work function, so it's not going to help. So James, what must I do?
You need to change the light, because if you change the color of the lights, you go more left, the frequency is going to become shorter, which means it's going to have more energy.
The frequency shorter.
Yeah, smaller.
Frequency. What are you sure you're using the right word? Is it frequency or is it
wavelength? Sorry, wavelength.
Please
wavelength.
don't use the wrong word there. Frequency can't be shorter or longer. Wavelength is going to be shorter or longer. Yeah.
You got what I'm saying?
I
if
know.
you make that thing, make it blue right now, we'll should be in business.
Okay. Are we in business?
Yeah. Wow.
Okay. So let's put
Make it
this.
blue.
Let's put this voltage back to 0. Oops. There's it back to 0. Okay, so even here though, yes, you're saying make it blue. Okay, I'm making it blue. So the wavelengths become shorter, which means the frequency goes up and the energy goes up. So now you can see electrons are being emitted. So what happens now is that I'm sending photons in this blue light that has enough energy to overcome the work function. So that means the threshold frequency of the red light is higher than the threshold frequency of this metal. Okay, so now you can see there are electrons moving. Now if I'm going to increase the intensity, now remember what I said before, intensity doesn't change energy, it only changes the number of photons. So we are back at you, Bianca. If I now go and increase the intensity, what do you think is going to happen?
There will be more like electrons being emitted.
Good. So if I increase the intensity, let's make it 100. Can you see that immediately there are more electrons being emitted because more photons are hitting with the right amount of energy. So now there's more electrons being emitted, but they're still moving at the same speed. So they're still taking the same amount of energy to be kicked out, and they're still using the same amount of energy as kinetic energy to move across, because I didn't put a voltage. If I now put a voltage, can you see what's happening now? What's happened? If I turn up the voltage, what's happening to the electrons? Anyone?
They emitted faster.
Now they're moving faster because I'm pulling them across to the positive side. Yeah, they were just moving because they had their own kinetic energy when this was 0. So this is their own kinetic energy that they gained from the light. So they absorbed their work function, and the rest of the energy they're using as kinetic energy to move across. If I put a voltage there, then I'm making them move faster. But what was interesting about this, and how they determined actually charges and stuff, is they went and said, okay, let's see if I can stop a photon. So that is how they did. You don't need to know this, but this is how they determined an electron volt, because what they did is they said, okay, let's put the voltage back. Now remember, these electrons are negative, so they're going to be attracted to a positive plate. So if they're being kicked out and I make this plate positive, so I'm swapping the polarity around. Can you see what's happening? I'm confusing these electrons. They don't know where to go. because I'm changing the polarity of the plates. So that, you will see there's another video that I will post. There's just a summary from one of the St. John's teachers, where he speaks about stopping voltage. Although it's not in your syllabus, how they determined 1 electron volt is they looked at 1 electron. So I'm going to actually, I've turned it off that. So remember, these are average energies of the electron. So if I click there, it's only the high energy electrons that are there. So now, if I turn it around, so let's look at one of the electrons. Okay, I'm going to have to be good. So let's look at the next electron that comes out. Okay, that one. And I get it. Ooh, I'm quite bad at this, hey? I'm trying to get one of those electrons to exactly stop. Okay, I'm going to, come now, stop. There we go. I'm getting that one almost, there we go, stopping. So that voltage there, can you see the 1 electron that's, oh, now it's moving again. That would be the stopping voltage, and that is what they use to determine the electron volt. But that's not that important for us now. What's important for us now is, if I use red light, it doesn't matter how many photons I send. I'm never going to have a photon that has enough energy to overcome the work function and to have the high enough frequency to have enough energy to overcome the work function to be kicking out an electron. The only way you can do it if it's not happening is by changing, let me just turn it down, by changing the energy of the light, and that means you need to use a new light with higher energy. And you can see at this, so that would kind of be the threshold where it just emits an electron. This is important for you're going to use exactly this for that alternative task that I'm giving you as in the exams. You know, there's a prac exam. This is exactly what you're going to do. It's going to give you jobs to do. So the wavelength that is just enough to kick out an electron. So you're going to have to move it to see where does it just start kicking out an electron. And if I take that wavelength and I put it into E equals hc over lambda, that will give me the exact work function of this metal, which at the moment is sodium. Okay, are you guys with me?
Yes.
Okay, if I want the electrons to have more energy when they leave, what do I have to do? So they're leaving now. What do I, okay, first they're leaving. Okay, let me use blue light. So now they're leaving, we know they're leaving. If I want more electrons to leave, what must I do?
Increase intensity.
Increase the intensity, because then I'm sending, and this is also an important question that they ask as an explanation. If I increase the intensity, I'm sending more photons per second in, therefore more electrons per second will be emitted. And if you look at the current, can you see what's happening to the current? The current has gone up. Oh, sorry, I'm using the wrong side of my pen. The current goes up now. If I turn the intensity down, the current goes down, because you need to remember what current is. Current is rate of flow of charge. So here comes the electrons. How many electrons per second is going? And at the moment it's pretty low. If I take up the intensity, now more electrons is going per second. Remember current, Q over T. So the charge per second is getting bigger, and therefore the current goes up. Very common question to be asked as well. What happens if I increase the intensity? If nothing was happening, nothing will still happen, because that means there's not enough energy to even emit one electron. So it doesn't matter how I change the energy, nothing is still going to happen. But if something is happening, if electrons are being emitted, then if I increase the intensity, I am sending more photons, so therefore I will have more electrons, and my current will go up. But my energy isn't changed. So all those things you must make sure when you answer the question that you don't mix up energy and current and all these words, but we are going to practice it at the end of chapter examples. Okay, so the FET worked. I'm so happy. Alright, I'm going to stop this and then, oh, not stop it, I'm just going to stop sharing it, and then we will look at the start looking at the calculations. Alright, so this is where we were on Thursday. So we said exactly this again. So I'm just going to write down the equation again. I know the video did it, but just so that we know, the energy that comes in is the energy from the photon. That energy, part of it is absorbed by the electron that's sitting there inside the metal needs to just be released and in our example that was the 100 joules. So that is the work function that the electron takes for itself to be released, and then whatever extra energy it has will be converted into kinetic energy. So this is the equation that you will find on your information sheet. You actually have all the other equations, but they don't tell you how to use it. You need to figure out how to use it, because as I said there before, they're not going to always give you the energy of the photon. They're going to give you the wavelength of the light. If they give you the wavelength of the light, then how are you going to get this energy? Please help me, Carly.
Use C equals, energy equals HF.
Okay, if they give you the frequency, then you'll use E equals HF, yes. And if they give you the wavelength, what are you going to use then?
E equals HC over wavelength, lambda.
Good, HC over lambda. So read your question nicely. If they give you the frequency, you're using this one. If they give you the wavelength, you're using this one. If they give you the energy, leave it. Leave it like that. And that's actually the one that people mess up the most. They go and change the equation if it's not even needed. Then for the work function, if they give you the work function, you leave it like that. You leave it work function. If they don't give you the work function, but they give you the threshold frequency of the metal, what are you going to change it into then, to me?
Equal to H times F.
HF, but this F is a special F, remember? If the work... Sorry?
I was just saying HF and then like subscript 0.
Good. Because it's a threshold frequency. So the work function is equal to HF naught, which is the threshold frequency. But if they give you the work function, please don't go and mess with it. These two are connected to each other, but they're not the same thing. And then the last one, Kivan, if they ask you for the kinetic energy, you'll leave it like that. But if they ask you for the speed of the electron, what are you going to change EK into?
If you're asking for speed
of the electron, and you only have the kinetic energy.
I'm not sure, ma'am.
What's the equation for kinetic energy? I'm sure you know.
Half mass velocity squared.
Yeah, you do know it.
Oh, that's what we do. I thought it was a trick question.
No, it was just in the video as well. No, if you want the kinetic energy, you're just going to use the same equation we've been using since grade 9, half mv squared. And the only thing that you need to remember is that this is for an electron. So they're not going to give you the mass of the electron. You need to go and find the mass of the electron, and it's on your information sheet. Please go and find it for me on your information sheet, James, and tell me what the mass of an electron is.
I got you. Just give me a second. Magnitude, that's charge. Mass of an electron is 9.1 times 10 to the minus 31.
What? What's the unit?
The unit is kilograms.
Okay, we always work in kilograms for physics. So can you see how little it is? It's like 0.0000031 zeros, 91, or 29 zeros, 91. So it's very, very small mass, but that's again why I'm always saying for this chapter you must just work with your powers of 10 correctly. So do not think they don't give you the mass of an electron. The mass of an electron is on your information sheet. If you already calculated your kinetic energy, then it's easy to go and get the speed of the electron. You've done that before in normal mechanics questions. You can do that. Okay, so this is what we're now going to practice. We still have 5 minutes, we can do it. Actually, no, should we just leave it for tomorrow? Because I now want to go to your textbook.